You know that feeling, right? You write some code, it runs, and hey, the job gets done. But then you look back at it and you just know it could be better. Well, today, we're going on that exact journey, transforming code that just works into code that's professional, efficient, and frankly, something you can be proud of.
Yeah, we've all been there. You get the right answer, but when you look back, your script is this tangled mess of repeated logic and sluggish performance. It works, sure, but it's brittle, it's slow, and it's a headache to maintain. That is the exact problem we're going to solve today.
All right, first up, we're going to tackle the #1 cause of messy code, repetition. The key here isn't to work harder or write more code, but to build a smarter, more reusable structure for all your logic. Functions are your absolute first line of defense against that repetition. So instead of copying and pasting the same lines of code over and over again, you package that logic up into a neat little function. This is the whole write once, use everywhere philosophy in action. It's not just cleaner, it means if you ever need to fix a bug, you only have to fix it in one single place. That's huge.
Now let's level up that structure with a little something called object-oriented programming. I want you to think of a class as a blueprint. Not for a house, but for anything. It's not the thing itself, but it's the detailed plan that defines what every single thing built from it will have, its parts, what it can do, all of it.
And here's where that abstract idea becomes totally concrete. The class is the concept of a car. It defines that, a car has wheels and an engine. The object, on the other hand, that's the real thing. That's the specific red Tesla Model 3 sitting in your driveway. This is the core of how we model the real world inside our code, moving from a general idea to a specific instance.
Great code doesn't just work when everything goes right. It has a plan for when things go wrong. And that's where exception handling comes in. It's your safety net. You try the part of your code that might fail, you accept any specific errors that might pop up so you can handle them gracefully, and then, in the finally block, you run your cleanup code, like closing a file, no matter what happens. This is what makes your programs resilient instead of just crashing.
Okay, so we've organized our logic. Fantastic. Next up, let's talk about organizing our data, because choosing the right container for your information can have a massive, massive impact on performance.
So let's compare two of the heavyweights here. On one side, you've got tuples. Think of these as your reliable guards. They're immutable, which is a fancy way of saying they can't be changed once they're created. This makes them perfect for protecting data that needs to stay constant, like, say, GPS coordinates. And on the other side, you've got dictionaries. These are the speed kings. They use a key value system that lets you look up data incredibly fast.
So why are dictionaries so blazingly fast? Well, the secret sauce is something called a hash map. When you look up a key, a special hash function instantly converts that key into a direct memory address. So instead of searching through a long list one by one, which we call a slow ON operation, a dictionary lookup is nearly instantaneous. We call that O1, or constant time. It's a perfect example of how choosing the right data structure solves the problem of slow code. We've made our code smarter, we've picked the right containers, but what happens when we scale things up? I mean, way up.
All of a sudden, even your most elegant Python loops start to feel sluggish. When you're working in data science or AI, you're not dealing with 100 items. You're dealing with millions, maybe billions. And standard Python lists, well, they just can't keep up. This is where we need a specialized tool.
And this table right here says it all. A Python list is flexible, sure, but it's really just storing pointers to objects that are scattered all over your computer's memory. A NumPy array, on the other hand, stores all of its data in one single, continuous, unbroken block of memory. And that dense packing is the secret to its incredible speed. How much faster, you ask? Well, get this. In one test, adding two lists with 1 million elements each took 0.05 seconds in pure Python. NumPy did the exact same operation in 0.002 seconds. That is 25 times faster. That's not just a small improvement, that is a complete game changer. This incredible speed comes from a concept called vectorization. Instead of using those slow Python loops, NumPy performs mathematical operations on entire arrays all at once, directly in super optimized low-level code. It's exactly why NumPy is the non-negotiable engine for pretty much all modern data science and machine learning.
All right, to wrap things up, let's cover a couple of finishing touches that really separate professional-grade code from a hobbyist script.
I'm sure you've seen this line everywhere in Python code. It's basically Python's official entry point. Think of it like the big green run button for your script. The code inside this block will only execute if you run this file directly. If another script just imports your file to borrow one of its functions, this code won't run. It's the key to making your code modular, reusable, and truly professional.
And that really brings us to our final takeaway. All of these techniques, functions, classes, exception handling, and high-performance libraries, they're not just about making code faster. They're about making your code smarter. Clean code is smart code because it's readable, it's scalable, and it's resilient. So the next time you write a script, ask yourself, is it just working or is it working smart?